What we are going to talk about today is the nature of the figures formed by circles and dots. We divide the discussion into three situations. First, 2 points and 1 circle. Second, 2 circles and 1 point. Third, 3 circles. We'll start the discussion from 2 points and 1 circle. In 2 point and 1 circle, we discuss the minimum circumscribed radius formed by 2 points and 1 circle. B and C are two fixed points. D is a moving point on circle A. Let the angle BDC be alpha, and then according to the law of sine, because BC is a fixed value, so when the alpha is closer to 90 degrees, the sine alpha is larger. So the radius of the circle passing the BCD will be smaller. When drawing with GeoGebra, which is a sketch software, we found that the locus of the circumscribed circle center point O, formed by moving point D around circle A, is a straight line, which is the one seen on the screen. It can also be found intuitively from the picture. If this line has an intersection with BC, then this intersection is the center of the smallest circumscribed circle. At this time, BC is the diameter. If not, then BC will be the chord of circle O, so it will not be the smallest when point O is closer to BC, because the length of the chord BC is also closer to the diameter. The circle becomes smaller. Then we discuss the situation of two circles and 1 point. First, let's assume that the relative positions of the two circles and the point are shown in the picture. The two circles are separated, and the moving points D, E, and C of the two circles cannot form a straight line.
At first, we also want to use angle to find the smallest circumscribed circle of two circles.
But because we have two moving points,
the angle and length form were not fixed. We found that this method is more difficult to discuss. Later, based on our assumptions, we intuitively believe that the smallest circumscribed circle should occur when circle O is circumscribed to circle A and circle B, as shown in the figure. But after actual attempts, we found that this is not necessarily the case. Under certain circumstances, the circle O and circle A will be tangent to point D, and the smallest circumscribed circle will be produced when the circle O and circle B intersect at 2 points. At this time, point E is located at any point on the two intersection points. Because of this situation,
the point D is fixed.
So it is similar to the case of 2 points and 1 circle, so it can be found by the law of sine.
Point E can produce the smallest circumscribed circle.
But if the circle formed by DA as the diameter has no intersection with circle B, then you cannot use this approach.
We used the method that we find the locus of the center of the circle in 2 points and 1 circle to find the locus of the center of the two circles and 1 point. And then we found the smallest circumscribed circle.
We try to use graphics to find the relationship between the center position of circumcircle and the moving point, as shown in the figure.
The locus of the center of the circle was too strange at first.
We saw the position of the center of the circle was irregular, but in an accidental situation, we draw out possible positions of the center of the circumcircle, and it is found that its center is actually limited to a certain range. This range seems to be composed of multiple curves. According to what we have learned, we use the circle equation and the parabolic equation to go. simulating the situation where the center of the circle is rounding. The results are unproductive. Later, in the online mathematics forum, we discovered the term hyperbola. After learning about its graphics, we combine our observation. The edges of the graphics seem to be symmetrical to each other after extending along the trend. So we turn the research direction to hyperbola. We extend our imagination to the forward side of the graph, and then according to the hyperbolic equation, the absolute value Pf1 minus Pf2 equal to 2a. Replace it with the form we want.
Let f1, f2 be the focus and 2a be the radius of circle A to make the hyperbola.
The absolute value Pa minus Pc equal to the radius of circle B, and then another hyperbola is set to the absolute value Qb minus Qc equal to the radius of circle B. We find that when the circumcircle is tangent to any circle, the center of the central circle will be on the hyperbola. Therefore, it can be deduced that the four vertices can be four situations. 1. One circumscribed and one inscribed. 2. One inscribed and one circumscribed. 3. One circumscribed and two circumscribed. 4. Two inscribed. If they are not on the boundary, they will not be tangent to any circle. Next, we have to prove that the center of the circle must be within the boundary. First, the center O of the circumscribed circle will be on the plumb line of EC. When the property of the plumb line, we can know that the absolute value OA minus OC equal to the absolute value OA minus OE. And with triangular inequality, we can know that the absolute value OA minus OE is less than or equal to AE, and AE is equal to the radius of circle A. So point O must be located inside the hyperbola P, and the same goes for hyperbolic Q. Since the plumb lines are all located inside the hyperbola, the intersection point, circle center O, is located within the range enclosed by the two hyperbolas. The range enclosed by the hyperbola is exactly the irregular figure we saw earlier.
Since the inside of the graph represents the locus of the center of the circle,
the vertex closest to point A will mark circle O have the smallest radius.
Finally, we are going to the part of the three circles. We have not yet found a way to prove the smallest circumscribed circle of the three circles. But our intuitive preliminary guess is that it is also circumscribed to the three circles. Later, we also imitated the method of two circles and one point to find
the locus of the center of the circumscribed circle
surrounded by three circles, and found that it is also a figure composed of three hyperbolas. Therefore, we are further searching for the three hyperbolic equation function. We found that as long as the 2a behind the hyperbolic equation is changed to the sum of the two radius, the range of the center locus can be found. But this method cannot find the smallest circumscribed circle. So we changed the 2a behind the hyperbolic equation to the absolute value of the difference between the two radius. At this time, we can find that three hyperbolas have two common points, and the 2 points are either externally tangent or internally tangent with three circles. This is the end of our report. Thank you for listening.